Alright, hell yeah, this is problem 1.31, problems in general physics, and we're just going to go over like the 2-minute to 5-minute solution of this. Now, we're trying to figure out just how to guess answers so we don't make mistakes. So what we have here is a ball that falls on an incline. And I guess what we just have to know is that if here is the normal direction to the incline, just like a pool ball, it comes in at this angle and leaves at this angle. You know what I mean? And guess what? The angle of the incline is this angle. I'm not going to go over that right now, but let's just say it is. We're just going to choose a value of alpha is equal to 30. Because if we do, heck yeah, this is 60, and then we have an outgoing angle of 30. You know what I mean? Now for the problems, I use this alpha as 2 alpha, you know what I mean, for my kinematic equations. But for this one, you could just be like, hell yeah, we got 30. And then so I pick a velocity of 20 meters. And the reason I do this because sine of, if I am got this sine of 30, sun is shining on the sine, and this has to be half of that. Sweet. And then I use an approximation that instead of this is 0.866, which would be the cosine of 30, we're just going to say, hell no, it's just the whole thing. That's a pretty decent approximation. So that's our approximations to get going. Velocity is 10 meters per second going up, half of our final. You know what I mean? And then definitely you need the energy equation, and we do that a little bit later in the video. But hell yeah, we just want a quick understanding of how we can get a guess of how far this thing is going to land. That's the question. How far down the incline is it going to land? So then the first thing that I do is just like, well, forget the incline. How about where it meets the horizontal again? You know what I mean? And we can just set that up. If we have 10 meters per second in the upward velocity, gravity is going to kill that in 1 second. It's going to go from 10 meters per second to 0 in 1 second. That's what this equation says. So it's 1 second up, 1 second back down to the horizontal. Sweet, that takes 2 seconds, and so that's kind of what I have written here. And if our velocity is 20 meters per second in the x, hell yeah, it's going to go 40 meters. So right here is our first check on reality, that for sure this distance has to be greater than 40. But hell yeah, it's something to work with. So then the second thing I did is just like, well, could it be double? You know what I mean? Try to think about that. You know what I mean? Could it be 10 times this? Hell no. You know what I mean? But could it be double? Maybe. You know what I mean? So that's kind of what we, this is the final answer. But like down here, I'm just like, well, could it be, the first answer we get is 40 and the second is 80. Now, I'm just going to go over the kinematic equations, not derive them, because we want to make this fairly short. But here's the kinematic equations for the x. You know, at any given time, at 1 second, here's my distance in the x. Well, duh, that's just going to be 20 meters times 1 second. It's going to be 20 meters away. You know what I mean? So that's what this equation says. Now, it is true, this is sine 2 theta. 2 alpha. So obviously this would be sine of 60 or cosine 30, which is that 0.866. But for our problem, we're just estimating this to be 1 just to get going. Okay. And that was the just to get going problem here. And actually, so this is fascinating because in the video I thought I kept with this value. And I didn't. No, we actually used the true values. So actually, we have a very good approximation. So let's get to that. Okay, so this problem, how you have to set it, you have to find the equation of this angle. You know what I mean? How we figure out where it lands in the horizontal is that we just set our kinematic equation up in the y to be 0. That's when it's going to hit the horizontal. And then it's really easy to find t. If this is 0, hell yeah. 0 satisfies, that's where it's at the horizontal, and then it's quadratic, so there's just one other location. But the second this becomes negative, oh, hell no. I mean, you actually have a quadratic that we just throw into our calculator, and we'll get to that in a second. So to find the equation of this, it's y is equal to mx plus b, equation of a line. It goes through the origin, so this is just y is equal to mx. What's our slope? Our slope is going to be negative yx. And what we do know is that tangent of this angle is y divided by x. So you can just really easily see that if the slope is negative y divided by x, we have negative tangent alpha. Now that's not the part that we're actually trying to get to. You know what I mean? We're just assuming we know what the hell is going on. We just want to find an approximation. I mean, we just want to then intuit to see if we can actually get this distance without like really just plugging and chugging all this in with the letters. That's too complicated. You know what I mean? Just so many places to make mistakes. So if we throw in that x is equal to 40, it takes 2.3 seconds. You know what I mean? To get to the horizontal. But then what actually we do this. We say, okay, so if x is equal to 40, let's say it's out here, then we go down to satisfy this equation. You know, if x is equal to 40, our y has to be down here at negative 23. And if our y is down here at negative 23, then we have to get a time for that to actually do that. And that time is a lot slower than just 2.3 seconds. Okay, well actually we step back. Holy Toledo. How did we find this? Well, we actually found the true value of the time in the x direction. If we said x is equal to 40, this is the time it's going to take. So we take 40 divided by our velocity initial, sine of 2 alpha, which is sine of 60, and we actually get that time. And so I did this 100%, and we get 2.3. But if that's the case, to just get to 40 meters in the x, and we're just assuming that our y has to be down there to satisfy this equation, that's going to take 3.37. So obviously that's not our x, and this isn't our y. But then let's just totally double it and get to 80. Sometimes you can kind of luck out. And if we did that, if this is 80, we divide by 20, divide by sine of 60, and we get our time of 4.62 seconds. Cool. Now if this is if we're at 80 meters, you know what I mean, to satisfy this equation, where we hit, we need to find our y. So negative tangent 30 times 80 is our y, and that's negative 46.2. And so then if we throw that into this equation, and what we do is I say this is, in my calculator, is negative 5, basically negative 5 x squared plus 20 cosine 60 times x, and then minus that y value. And I already have that in, and then we can graph it and then actually find that time value using our solver. So that's what I did there, and we get 4.2. So like, all right, so now we're getting closer, but we don't know if we overshot it. So I guess just to make the problem simpler, I did that at, I went up in increments. I went to 50, and it took 2.89 seconds, or 3.6. Then I went to 60 and did that process. It took 3.46 seconds, and then 3.82 in the y. And then I went up to 70, and hell yeah. So we're getting closer, you know what I mean? So 2.3 is pretty far away from 3.4. Getting closer here, and then at 70 meters we get 4.04 seconds and 4.01 seconds, and hell yeah, so that's it, you know what I mean? At x is, when it goes up with that velocity of 20 meters per second, it's going to be 70 meters in the x, and then down 40 meters in the y, and because the time for those equations to do that are the same. So now we have a continuity, and then they want to know the distance from here to that point. That's just this equation: x squared plus y squared square root that. And how do we find that? Well, it's x is the y value, x value, and it's Pythagorean's theorem. This squared plus this squared square root that is equal to this linear distance, or the hypotenuse. Alright, and so we get this to be 80 meters. And even in the video, I thought for whatever reason, I was always estimating with that initial guess that the velocity in the x was 20. But no, well, once we actually got the real equations, this is a very solid answer. So hell yeah. Now if you want the long version, you can kind of just see me go through this. But why we're doing this is because what I want to do is derive this equation like it says. Like, hey, let's find an equation for distance with all these parameters, and it's just going to be one huge sloppy ugly equation, and it's just so many places for errors. I've tried it a couple times and I can't not make errors. So then I made this video of just like, well, let's choose the simplest setup, where, especially if this is 30, like there's such a cool trigonometry, such a cool value, because you know this is totally accurate, that the velocity in the y is just half of your total velocity, you know what I mean? So hell yeah. And then it's just so easy to work with. 1 second up, 1 second down, and then what's our velocity that way? You know, I mean, you kind of get it. Okay, and then we just use an iterative approach to actually just choose values to our x that satisfy that equation on the line, and then make sure that these time values have to be the same. You know what I mean? Instead of doing the grueling process of what you would do is you would throw this equation right into there, and this equation for x into there, and then you'd solve for t. And what a headache. You could do that. Like, it wouldn't be too hard. You could do that in your calculator just for one value. But if you're going to do it for letters, then you got to go through and sweep up and clean up everything just to make sure it's not a nightmare. And at the end of the day, still try to get the accurate answer. So that'll be for the next video. It is going step by step, you know what I mean, going through the process and using this as a check on reality to back it up. Because then I can say, I can input alpha is equal to 30, velocity initial is equal to 20, and whatever height that generates that initial velocity, and I should be able to get that number. And if I don't have that check on reality, then I know I've made a mistake, and then I can go find that mistake. But that's the whole point of this video, is like how do you take a problem and set it up in a way that you like it, so you visually can see when it's going to hit the horizontal, know that it's going to be more, and then you know what I mean, and then try out the continuities. You know what I mean? Well, is this the equation for a line? If it does hit this, you know what I mean, doesn't this equation have to be satisfied? Cool. And that's kind of what we did. And then, you know what I mean, and I'm going to state this before we go, is like, if you can't just throw in the numbers into an equation to get a couple values, and do that again and again and again and again. You know what I mean? The mountain climber approach, you know, it's like Price is Right. But if you can't do that 6 times without just losing your brain, you know what I mean? But you know, that's what we're showing here. It's just like, make it simple, throw it in, make sure you get accurate numbers, you know what I mean? And then start moving, you know, in a direction that you think. And shoot, you might move in the wrong direction, and then you got to go the other way. But this is just a cool technique to hone in on that answer without having to do a lot of algebra. Because where you do the algebra is where you're going to make mistakes. So that's the whole point of this, is to at least get one check on reality. So when we do the heavy algebra with just letters, we have something to double check. Alright, thanks for joining me. And guess what? That's a video. Alright, hell yeah. So we have problems in general physics. This is Irodov. This is problem 1.31. But let's just get to it. What we want to do is find a way to not make mistakes. You know what I mean? So, because this problem just has letters. And so at the end, we want to have an equation to find the distance just with letters. So let's go over the problem. So we have a ball, and it falls on a height, and then it impacts an angle. So I would always make your angle not close to 45. Like, even right there, I probably made it too big. You know what I mean? But 30 degrees and under, and we'll probably just start with an angle of 30. So they're saying that this is alpha. That's our angle. So we're going to drop the ball from some sort of height h. So that's the height h. Well, like obviously down to there. Sorry about that. And so yeah, so there's the ball. And so sure, it's gonna, because of energy, you know what I mean, we have a potential energy of mgh, and then right at impact, you're gonna have no potential energy, and then you're gonna have a kinetic energy of 1/2 mv squared. So cool, we're going to set those two equations equal, masses cancel, 2 comes up here, so we got 2gh is equal to v squared, so then we get v is equal to the square root of 2gh. Hell yeah, you know, a very common equation. And what they're saying, so we still have this angle alpha upon impacting, and then here's the normal. So anytime you have a slope, I would draw the normal to the slope. And maybe I didn't draw it very good, but there you go. So this is going to be a 90-degree angle. And now this is where I said, hey, probably make this angle a little bit less than... Alright, sorry about that. But yeah, try to make this angle definitely you know what I mean, smaller than 45, so you can actually see that if we have a 90-degree angle, you know what I mean, hey, this is the smaller angle and this is the remainder. And I would always say, like, you know, anytime you have two different angles, you know what I mean, hey, this is going to be theta, and that means this is like phi. If you use those two, you can't go wrong, because then 90 degrees has to equal theta plus phi. And then if you know this angle theta, well, you know phi. You know what I mean? Because you can say phi is just 90 minus theta. Cool. But yeah. So right here, how do we use geometry? So anytime you're trying to find angles, it's like, well, just start drawing parallel lines, and definitely 90-degree lines. And so, you know, one geometric axiom is that if you have this, you know, little Zorro shape, hell yeah, that means this is going to be alpha. If you have mirror images, you know what I mean, of angles, that means this is going to be alpha. Okay, hell yeah, so we're on a roll. And didn't we say that this is going to be 90 right there? So we have that. So I'm going to, like, for this problem, sometimes I'll say alpha is theta, because now we can have, this is our angle theta, and that means that this angle is phi. And then so we have that relationship. Okay, sweet. And if we know that, you know, this 90, you know, we're covered on that 90, and now we can go up to this line across and say, okay, we got another 90 degrees between, like right in here. So this is phi. So therefore, this must be theta, you know what I mean? And this must be alpha, because we're saying that alpha is equal to theta for that. Cool. So now, and if we know that, then we also know that, hey, this angle right here is also phi, you know what I mean? It is going to be 90 minus alpha. Okay, hell yeah. And I guess we need to draw this one more time. Because with this problem, like making the setup, and I'm even going to try to draw my the angle, this one, just a little bit less, just so you can make sure that you can totally tell. And then I'm going to draw the perpendicular. So see, if I draw a perpendicular here, here's alpha, there's alpha. And what they're saying with this problem, though, is that when we drop this in, we have a ball that bounces elastically off the inclined plane. Alright, so just like a pool ball, it's going to come in, and then it's going to, so here's the normal direction. So if we dropped it, you know, if we took the problem and made it horizontal, and you just dropped a ball on a horizontal slope, it would just go up and down. But because we're dropping it as some sort of angle to the normal direction of the inclined plane, it's going to bounce at that same angle, alpha. So that's kind of what we have going on right there. And this is the vertical, you know what I mean? So if we wanted to find, if we're saying that this is our velocity of, you know what I mean, the bounce, like, hey, this is going to come in at this angle and then leave at that angle. Our V naught, it now has a component from the vertical, there you go, and then from the horizontal. So you could either do this, you know, make your box. What I like to do is, like, hey, darken in this arrow as my vector, but then make the components kind of with dashed lines, and then with open arrows. So then I know that those are the components. And now we have an angle that we can use. You know what I mean? Essentially, this angle is 2 alpha. And, you know, I was like, well, could we say that this angle is, you know, how does that relate to phi? You know, I'm glad I did that, but for this problem, since we're going to get an equation with alpha, sometimes, you know, it's just a lot of problems will be like, hey, your angle is going to be from the horizontal, you know what I mean? But in this case, our angle is not from the horizontal. You know what I mean? We know our angle from the vertical, and we know that it's 2 alpha. So that's what we're going to use. And we can still find the components. So heck yeah. So if this is our angle and the sun is shining, then this component is the sine component. So the horizontal component. So we can say that this is v naught x. So our initial velocity in the x is going to be the total vector v naught times sine of 2 alpha. And then we know what our vertical, you know what I mean? In the y, our vy naught, I guess we would say that, vx naught. So our vy naught is going to be the initial velocity times, if this was the sine component, then heck yeah, this is the cosine component. This is the cosine component. So we have cosine of 2 alpha. Okay, hell yeah. And so this problem, you know what I mean, the setup's very crucial. But the place that I was making mistakes, and what does the problem actually say? They say when you drop it, it's going to have a velocity, and then when it bounces, it's going to bounce at that angle, you know what I mean, theta from the normal, so you have an angle of 2 theta, and then when that bounces with that initial velocity, it's going to be a projectile, and it's going to land. And you want to figure out the distance. We'll drop it right here. The distance, and then you're trying to find this distance of how far from the bounce that it landed, and to get an equation for that. Okay, and what we know about projectiles, so then the part that we just need to know for this problem to actually get a solution is one is that we know. You know, for this problem, we're just going to use the acceleration of gravity as 10. So we're saying the acceleration of gravity, I guess acceleration in the y direction is negative 10. Cool. And then we know that dvy dt, because this is the equation for acceleration, is the change in y, change in t, that's equal to the negative 10. And then we can integrate, and we get an equation for, you know, we separate variables, and then so we get dvy is equal to negative 10 dt, and then we can integrate. And then so this becomes an equation for vy as a function of t, and then we're integrating, you know what I mean, dt just goes to negative 10 t. Cool, so this is, but plus a constant. And then how does the constant work? Well, we have to say at time is equal to 0, so you'd go negative 10 times 0. Well, and this would be vy at t is equal to 0, or just vy of 0, you know, because we actually threw it in. We're going to have velocity in the y, and we already figured out what that was going to be. That's going to be v naught cosine 2 alpha. And so if this term goes to 0, so we have v naught cosine 2 alpha is equal to 0 plus a constant. The only way to make this balanced is our constant to equal this. So our constant is v naught cosine 2 alpha. All right, hell yeah. And my goal isn't really to actually go over the kinematics. But I mean, I guess we have to. So I mean and then so now we have an equation for our velocity in the y as a function of t is negative 10t plus v naught cosine 2 alpha, and then we can say that velocity, you know, in the y is dy dt. You know what I mean? So it's the definition of velocity. Velocity is change in position, change in time. And then we can, you know, put this equation into this side. And I would kind of just write it like this. So I would put this part. So I would say dy dt is equal to this equation, negative 10t plus v naught cosine 2 alpha. All right, hell yeah. And then we can separate variables. So I'll just do that by doing that. And then we can integrate dy and integrate this. And then we get a function of y as a function of t. That's what we're integrating. And we get 1/2 negative 10 t squared. This becomes t squared divided by 2 plus v naught cosine 2 alpha t plus a constant. But here, we're just saying this is 0. We're going to say this is 0x, 0y. Cool. All right, so our constant at time is equal to 0. Well, we're going to say y at 0 is 0. So we're covered there. Our constant is going to be 0. And now we have an equation for our y term. And cool. And you can do that same thing for your x. You know, acceleration is 0 in the x. That's going to be dvx dt is equal to 0. Separate variables. We got dvx is equal to 0 dt and integrate. And we get a velocity function is just going to be 0 plus a constant. And we know our initial velocity in the x is v naught sine 2 alpha. Okay, and then we can say that that is dx dt and separate variables. Do the same thing. We can get an equation for x, and it's probably better just to write this, you know, simply just, hey, this is my equation for y, this is my equation for x, and now my equation for x is v naught sine 2 alpha t. And again, our position at this initial, we don't have it. So at t is equal to 0. Our x is equal to 0. So we don't have a constant. Constant of integration is 0 on this one. And heck yeah, so now you have an x and y term. You know, and damn it, I need to stay on this page. This is not even getting to the part where I want. I'm just like, hey, can we just guess the distance? You know, can we throw in an initial velocity and guess? That's the whole point of making this video. But we're trying to go through the whole thing anyway, kind of at a slower pace. To see if we can to get the right answer every time and make mistakes. We definitely want to make mistakes. I have not done this one actually all the way through. I've worked on this one a little bit, but I haven't made it all the way through with actually getting my equation for D and making no mistakes. All right, so now we need a relationship. Because if we just had a horizontal and we have this projectile motions, well, we would just, the second it would impact, that's just going to be our y value is equal to 0. So we would just set this equal to 0 and find our time value. And then we would use that time value and throw it into our x equation, and then we would figure out our distance. So if our distance was totally horizontal, that is the simple way to go. But now we know that, you know, if y is at the horizontal right here, well, this is an inclined plane that's sloping, and so, you know, it can go farther in the y and then farther in the x, and we just don't know what that is. But even right there, we could figure out what our angle and our velocity components are, and then just solve it for that, because that would be an easier thing to solve. And that would at least give us a check on reality. That, like, the distance that we solve for there would have to be a less than our distance for the problem. So, like, this distance would have to be less than our distance p, distance for the actual problem. So that could be a cool check on reality. We will probably do that. But the actual relationship of this is when you really want to use, I think. I mean, the one way that I look at this is just like, well, you have equations. You want to look at this inclined slope as an equation for a line. You know what I mean? So then we say the equation for a line is y is equal to mx plus b. It's going through the origin, so our b is 0. But we need to find our slope. You know what I mean? And then so if this is all that we have to work with is our alpha, and you can either do it from both sides. You could say, you know what I mean? Hey, I mean, what we want, you should do the equation of a slope. Equation of slope is rise over run. Cool. And so we're actually going to be, you know, we're not going to go up. We're going to go down in the y and then over in the x. So for our problem it's going to be negative y divided by x. You know what I mean? And so if we knew that x term and this y term, we would be set. But we don't know the relationship between those, but yes, we do. So, I mean, based on trigonometry, and I'm going to slow down here just a little bit, because, what we have here is x, y, and then alpha. And then let's say our hypotenuse is 10. Let's say we actually do know it. You know what I mean? And our angle here is 30 degrees. Like the three things, the three like most basic things you need to know. Actually, maybe four. I guess the first is Pythagorean's theorem. Is that, hey, these sides, you have x squared plus y squared is equal to your hypotenuse squared. Cool. Like that's the first one. The second one are going to be your sines and cosines. What they say is like, hey, you're always interested, you're always usually knowing something about the hypotenuse. It's usually like an initial velocity, or like that's your vector, and you want to figure out what your components are. And your components always have to be less than your hypotenuse. They can be equal to your hypotenuse if you don't have any angle and you just have like a horizontal line or a vertical line. But let's get real, and those would be super obvious. So if we have any sort of angle, like these components are always going to be less than your hypotenuse. And that's where sines and cosines shine. And we're just looking between 0 to 90 degrees. Like obviously this angle could be 0 and it could be 90. 90 is totally vertical, 0 is horizontal. So we're not going to focus on the 0 and 90, but just any angle in between. What we want to know is like, hey, look at this. And at a 30-degree angle, you have relationships that are just easy and obvious. Like, hey, look at this distance. So visually, I just say, hey, look at and what the hell am I comparing? I'm comparing this distance to this distance. Hey, let's take this distance and just chop it in half. You know what I mean? Whoa, this distance looks exactly like that. So we can really just visually say that that's 5. Now over here, this is where it is good. I use the approximation that if you're dealing with like a 30-degree angle, like your cosine component, just approximate it to 100%. Like it's 1. You know what I mean? It's 0.866. That's cosine of 30. But just look at this. This looks like 10, and you can say, hey, that looks like 10. You know what I mean? You're not too far off. Like obviously that's a poor approximation, but it's a good one to do because it just is. Okay, hell yeah. So let's say we just did that. You know what I mean? Let's say we just said, hey, this was 10 and this was 5. Don't we have an equation for slope? I mean, just right off the bat, we know we're going down 5 and then over 10. And so our slope is going to be negative 1/2. You know what I mean? And that's kind of what we see. Down 1 over 2. Like, isn't that visually what we see? I mean, it's not 100% because this isn't down 1 over 2. This is 5 and this is... anyway, this is, if this is 5, this is 8.66, and you're going down 5 and then over 8.66, so we could do that. You could say negative 5 divided by 8.66, and our actual slope is negative 0.5, who cares, you know what I mean? That's what I'm getting at. Like, at the end of the day, you want to find simple things to make approximations so you can't mess up. And this is one of them. 30-degree angles, hell yeah, we always know that the sine of 30 is 0.5. Well, just in your mind, just think cosine of 30. Hell yeah, we're just going to approximate it. It's just the hypotenuse. You know what I mean? And that goes a long way. You know what I mean? It does. It definitely goes a long way. So now we're going to start getting into the guesstimations. Like obviously the right answer for this is and what did we just do? Because you don't, like, if you know sines and cosines, you don't even need to know what the hell the tangents are. Like, didn't we just solve for x and solve for y? Like, you could, we said that this component was going to be the hypotenuse, you know what I mean, 10 sine alpha. And then this over here was going to be 10 cosine alpha. And then we said that the slope was going to be negative 10 sine alpha divided by 10 cosine alpha. Well, look at these 10 values. Those just cancel out, and we get negative sine alpha divided by cosine alpha. And even if you just got to here, call it a day. You don't need to know anything about tangent. But definitely that's the third thing. If you're only going to learn 3 things, and obviously 4, you got to remember Pythagorean's theorem. It's just something that you forget, and you're like, oh, no, duh, that's going to make life so easy. Okay, so the third or fourth thing, I guess, is to know that tangent, and it's pretty straightforward, it's just the sine component divided by the cosine component. Well, that's exactly what we just did, sine divided by cosine. So now we can say, and what is it? So we're saying the tangent of the angle is going to be the sine of the angle divided by cosine of that angle. Cool. And, and honestly, I don't even know why I did that. Like, obviously, this is tangent, but you want to know tangent of like this. Hey, tangent is just the, tangent is the sine part, that's the x part, divided by the y part, see? So that is your tangent, that's x divided by y. And now if we go up to our slope is negative, holy hell, and I totally apologize. Like, man, I messed this up from the start. This obviously is our y direction, and this is our x direction, you know what I mean? But that's why we do this, you know what I mean? We make mistakes, and you probably catch them way before I do, or just get hella confused. But for sure, so this is my y component, this is my x component, and so the tangent of this angle is going to be y divided by x. So we have tangent alpha is y divided by x, and then I go up to my slope. My slope is rise over run, but we're going down, you know what I mean? My rise is actually down y and then over x. So my slope is negative y divided by x. And right here I have an equation, tangent of alpha is y divided by x. So now I know my slope is negative y divided by x, which is just a negative sign on this. So my slope is negative tangent alpha. So there you go, I'll write it again. Slope is negative tangent alpha. And now I have an equation for my line that says y is equal to the slope, just found it, is negative tangent alpha times x. And then my b term is 0 because we're going through the origin. So hell yeah, so this is the continuity for this problem. It says, hey, we determined our y position of this projectile, and we determined our x position. At any given time, this is my x and y, you know what I mean? And so if we're saying it does impact the plane, well, it has to satisfy this equation, you know what I mean? Because this is the equation for every point on the line, you know what I mean? So if a projectile hits it, it has to satisfy this equation. So what we do is we take this x term and throw it right into there for this x, and this y term, and then throw it right into there. And then we solve for our t. Cool. And when we solve for our time value, then we can then what do we do? So obviously if we throw x and y into there, we get our time, and this is going to be time for impact. Once we know our time for impact, we can go back to these equations and then throw that time in. So we can get an x position and a y position. So our x position is going to be some positive number, and then our y is going to be some negative number, and that's going to be our position at impact. But it says, what's the distance from the point of bounds? And so then, like, you know, I mean, draw another line. Well, we're going to know this x distance, and we're going to know the y distance. You know, we're starting from the origin. So when we throw in t impact for y, that is this point in the y, and the same thing for x. So this is xy, and then hell yeah, like what did I say? We need to know 4 things. So you definitely need to know Pythagorean theorem. This distance is, you know, a squared plus b squared equals c squared. So if you're trying to find your hypotenuse, you know what I mean, your c squared, then you take, you say, you know what I mean, a squared plus b squared is equal to c squared. We're trying to find c, so c is equal to the square root of a squared plus b squared. And in this case, you know, our distance, our c is our distance, and then these values are x and y. So here's our equation, x squared plus y squared. But it's just fascinating, even even going through like first, second, maybe even third year engineering of just even knowing that this equation, you'd be like, holy hell, you should be using this equation just on the daily. You know what I mean? The fact that, oh, if I know my x and y coordinate, you know what I mean, and I'm starting from, you know, a zero value, oh, hell yeah, you know what I mean? And even if you weren't solving from a zero value, it would just be the change in x squared plus the change in y squared. It doesn't get too heady, but you'll be able to find the distance between 2 points. I don't know, you know what I mean? Just knowing that the equation of a line is y is equal to mx plus b, that was critical for this problem. Knowing that the distance, you know what I mean, obviously it's Pythagorean's theorem, and but yeah, even and then just finding the equation for this line based on that alpha. You know what I mean? Figuring out the slope, and that was a tangent relationship. Didn't have to be a tangent relationship. Obviously, you could just say it's a negative sine divided by cosine relationship, even if you didn't know anything about tangent, but that's the definition of tangent. All right, hell yeah. So where we're going to go from here is that still doesn't give us any information about what that distance could be. You know what I mean? Inputting some sort of velocity. So now I'm going to stay on this page, even though it's heady for me even. But we want to figure out something. I was thinking. So what happens is that I have a video of me throwing up a baseball. I don't know if I'm going to include it like right here. Hell no, probably not. That would be too much work. But if I do, I can throw a baseball up. I think I can throw it up for, oh, maybe just a second. I don't know. Can I throw a baseball 40 miles an hour? I think so. I bet you a person can throw a baseball straight up 40 miles per hour. And what you know about acceleration of gravity, it's negative 10 meters per second. So, I mean, if something's going, if you throw with initial velocity of 10 meters per second, that's 10 times 0.25. That's 22 miles, basically 22 miles per hour. It's in 1 second, it's going to have zero velocity. It's going to be stalled out. So it's going to be 1 second up, 1 second down. So that gives you kind of a time frame, you know, on what's going to happen there. And hell yeah. So, like, I'm not worried about this height right now. Like, obviously, if you've done some of these problems, you know that if you have a 5-meter height, that is going to generate, it's going to take 1 second for that to actually drop and impact. And if it takes 1 second, that you'll know because of acceleration is negative 10 meters per second per every 1 second, then you're going to have a speed of 10 meters per second. You're going to have that 22 miles per hour even at a height of 5 meters, you know, I mean 15 feet. So that's pretty interesting. But now I'm just saying, is that all we want? Do we just is that going to be good enough if we just say, hey, we're gonna have an impact of 10 meters per second? And so yeah, I think I'm pretty satisfied. But now, like, how do we get good on this angle? Because this was going to be this, like, okay, check this out. So this was going to be 2 times alpha. I'm just trying to find ways to kind of simplify this. So if we said our alpha is 30 degrees, this is 30, this is 30. Well, this remainder has to be 30. You know what I mean? So we're actually, this thing's bouncing just at a very horizontal angle. So that means that the vertical component, the Vy component, is just going to be half of V naught. We already know that because we know, you know what I mean? Hey, if this is 30 degrees, the sun is shining on the sine, and the sine component is only half at 30 degrees of the initial vector. And if we use this scenario that at 30 degrees, hey, this vertical component is just the total vector, well, hell yeah. So now we're just going to say V naught x is equal to 10 meters per second, but then our Vy naught is equal to 5 meters per second. But that's where I didn't want to do an initial velocity because of this, because I wanted to do 20. So we're going to say 20 meters per second. So now we're going to have to go up, we'll probably have, I think the way this works is you have to go up like 15. You have to be at 15 meters to actually generate, but anyway, because things move hella fast. But anyway, that's the kinematic equation. But anyway, we're just going to say, hey, the height at which it's going to take a change in time of 2 seconds to fall, that's what we're interested in. And we know the acceleration of gravity is negative 10 meters per second per every 1 second, and we're gonna drop it for 2 seconds. So that means that we're gonna have a velocity in this direction of 20 meters per second, and then it's bouncing elastically. And so we're not gonna lose any of that velocity. It's just gonna be at a different angle. But we're going to have 20 meters per second. So that's where I'm saying that. And we already know our angle. We're dropping in vertical, but because of this slope is 30, we have to take the normal to the slope. So this is 30, and then we have to, like a pool ball, we have to mirror image like the normal direction. So if this is the normal direction, I definitely want to reiterate that, because and this is something where it's just like I don't know how to prove that. You know what I mean? I actually don't. Like, I actually want to just do it by experiment with a camera, and just to make sure, like, I want to get an angle, you know what I mean? And then drop a ball horizontal, and then have a line for the normal, and then just see that the incoming angle is equal to the outgoing angle. But hell yeah, if we do that, we still want our angle related to the horizontal. But in this case, we want our angle related to the horizontal, and that's just going to be 30 degrees. It's easy to work with. With the actual problem, we'll definitely take it to be 60 degrees. And that ain't too hard to work with either, because, you know, if this is 60 degrees, hell yeah, my sun is shining, and now we have sine of 60. Well, sine of 60 is that 0.866. Sine of 60 is the same thing as cosine. Oh, am I getting that right? Sine of 60, yeah, is the same thing as cosine 30. You know what I mean? So if this is 30 and we got cosine, yeah, that's 0.866. Cool. And then the cosine of 60, well, hell yeah, that's 0.5. You know what I mean? So yeah, and it's due to that relationship. You know what I mean? But we won't get into that. We're just trying to actually just figuring out how to get the problem set up so we're not going to make mistakes, you know what I mean? So we're going to say this is 20 meters per second. Now we have an upward velocity of 10 meters in the y, 10 meters per second. And then hell yeah, we're just going to say this in the x is 20 meters per second. So now the problem gets real simple. And we're gonna totally neglect the plane, and we're just going to say it impacts on the horizontal. So right now we're using no kinematic equations. I mean, we're basically using the kinematic equations in our head, but we're doing so from just a practical perspective. If we have an upward velocity of 10 meters per second, gravity is going to slow that by 10 meters per second every 1 second. So we know in 1 second, this thing is going to stall out, and it's going to be at its vertical. And then we know by symmetry, it's going to take another second for it to fall back to the earth. So to impact the horizontal, let's say it impacts an angle, but then right here is just a horizontal ledge that it's actually going to hit. We're going to say that's going to take a time of 2 seconds for impact. Well, now we just go back to this equation for our velocity in the x is 20 meters per second. So if we had 1 second, it's going to go 20 meters. If we have 2 seconds, this says it's going to go 40 meters. So right now we have not used any equations. We're just, hey, we're pretty good with speed. 20 meters per second times 2 seconds is 40 meters. So right now, with an input of 20 meters per second for our initial velocity, or after we solve the energy equation, if our velocity, and oh, check this out, we can actually solve this right now. If this is 20, what the hell is our height? Well, that's going to be 20 squared, and then divided by 2g. So we have 20 squared divided by 2 divided by 10. And hell yeah, we get a height of 20 meters. Oh yeah, it's an additional 15. So if we go up 5, if we want another second, we got to go up an additional 15 meters. I remember that. Change in x would be an additional 15. Total height of 20. So now we're cooking with some oil. And we just found that our distance at impact from the horizontal is 40 meters. So sweet. So now we have that first check on reality that when we actually do the problem, if we input a height of 20 meters, it's going to generate a velocity of 20 meters per second. That's just the way it turns out. 2 times 10 times 20 and the square root of 400. is going to be 20. Yeah, it's just nice numbers. But that's exactly what we're doing. We're trying to find the nicest numbers for the problem, so we won't make any mistakes. All right, so we know that it doesn't hit the horizontal. It actually goes farther, and it's going to be down on the vertical. We don't have any check on reality on that, but we do know that it's going to be farther in the x. But now we do have this equation, you know what I mean? So let's just guess, you know what I mean? Let's say we think it goes 50 meters in the x. So now we can say, what's our y? That's going to be negative tangent of 30 degrees. Is that right? Yeah, 30. Yep, 30 degrees. Times, and am I in degrees? Hell yeah. So negative tangent 30, what the hell is that? Oh yeah, that's that interesting number. Yes, the slope. Cool. Times our x of 50, times 50. And so just to have some sort of number, hey, maybe our y is going to be negative 28.86. And yeah, and that might, and even right there, like how could we use those two numbers? So we're going to store this as alpha y, and then we're going to store 50 stored as alpha x. That was just a guess because it's going to be bigger than 40. Like even just from the iterative perspective, didn't we say these time values have to be the same? You know what I mean? So and this will be just a little bit harder. But we can find that we can say x is 50, so we have x divided by 20 divided by sine of 2 times 30. So this is our first time value, alpha t. Now for this one, we probably have to throw it into our calculator. So hey, this is why it's negative 28. We're going to add 28.86 over here. So, or basically we're going to subtract y in our calculator over here. And so alpha y in our calculator is negative that. And we're going to throw this into our, I hate Pythagorean theorem, so we're going to do this. We're going to go 0.5, negative 10, x squared plus 20 cosine 2 times 30, that's just 60, and then x. But then we got to subtract alpha y. We have that in our calculator. So now we're going to zoom 6. Oh, whoa, whoa, whoa. Oh, bummer. I don't know why I didn't like that. Okay, so, yeah, why doesn't it like this? So we have 1/2 times negative 10 x squared plus 20 cosine of 60. Yeah, we're good there. Times... times x minus, oh, it hates y's. Yeah, no duh. So alpha y, it hates that. So anyway, so let's get this value for y, and we're going to store it as alpha w. Sorry about that. Yeah, I totally forgot that if you're doing equations, you can't use x or y. So alpha w. Okay, booyah. So now we're going to zoom 6 this. I hate quadratic so much. So now we can just you know what I mean, go to value 5, and then find the 0 point, left bound, right bound, and then we have a 3.6. So we're going to, x stored as alpha s. So now we have alpha t, alpha s. Like obviously those do not jive. I'm going to get some more calculator juice, get some more battery juice in my camera. But all we have to do, you know, even from here, we have enough that we assume everything up to this point is 100% right. You know what I mean? We don't want to mess with any of the numbers to make any mistakes. And so all we're going to do is just going to readjust some of these numbers. We're just going to readjust our x value, maybe 55, and then solve it for our y. And then find those time values again and see if they get closer. And if they're equal, then hell yeah, we have a total check on reality. And that would be pretty cool. Alright, hell yeah. So, and this is the best part about mathematics and physics is like, hey, can you set up something and then just repeat it just a lot faster? So we said our x distance was going to be 50. Well, let's say it's 55. So there's our 55. We're going to divide it by 20. We're trying to solve for that t. And divide it by sine 2 times 30, we already know that's 60. Hell yeah. So we're going to, oh, and we get a value that's just a little bit better. So we're actually going to store this as alpha O, just so you can see our last value for t was 2.8. Now we got a value of 3.17. You know what I mean? Because when we threw in our y value, it was pretty big. It was 3.6. We want those to kind of converge together. Yeah. That's so fascinating. Because I think that there could be an iterative process. Because let's say we found this 3.6. Let's throw this in here just for kicks. So we have 20 sine of 60 times alpha s. So now this says our x our x value is 62 meters. We thought it was 50. You know what I mean? We found the time value. So all we're doing, like the cool way to do it, I think this is called Newton's method, or like, you know, Newton's method potentially is where you take these two and just average them. So we're going to go 50 plus 62 divided by 2, and we're going to go 56. So let's hella do that. So that's going to be such an improvement. Instead of just guessing and checking, we actually used a fundamental of like knowing that these things are overshooting in any way. So let's do it. So 56 divided by 20 divided by sine 60. All right, hell yeah. So now that's my alpha. That's going to be my t. I'm going to store it as alpha O. So my original t was 2.8. Now we got 3.2. Okay, so if this is my 56, my y is negative tangent 30 times 56. So this is my y. I'm going to store that as alpha w, obviously, and then just come back up here, and I don't think anything about this equation changes at all. We just have a new y, which we're calling w, and so we're just going to zoom 6 it, and then find the 0. I always do the value first. I hate, no. But anyway, I guess it's not too hard to just scroll to it. The calculator's a little bit slow sometimes. Okay, hell yeah, and so we got 3.7. So now we're gonna, that automatically stores as x, so we're gonna store that as alpha n. So now we used to have alpha s is 3.6, now we have alpha n is, 3.7. And then alpha o is 3.2. So maybe we're not doing super good, you know what I mean? But I guess so now we're gonna take that new. Sure, we'll do the same thing. You know what I mean? Take that new. Oh, you know what we should have done? I'm curious. Let's do this because we said that we had 3.6 out of this equation. So let's actually throw that into this equation. See what we get. We get 20 sine 60 times alpha s, and we get 62. So now let's use that as our new x value and see if it doesn't blow up but get more iterative. So let's do it. So now we have that as my x, so I'm going to times negative tangent 30, and then I'm going to store that as alpha w, and then zoom 6, and we're going to get the 0 value, left bound, right bound, and 0, and we got 3.8. I think it's worse. Store it as alpha I. So now we would have alpha. We were getting better with 62. Okay, so let's stick with that. So now we have alpha O and alpha N, and they're getting better. So now we're going to use this alpha N into this equation because alpha O was this. This was our time for alpha O, and but then we solve this one for alpha N. We're going to use that time value into this one. It's going to overshoot it, obviously. So we have alpha O sine 60 times 20. And now I have 56. Oh, whoa. Alpha. We need to do this. Sorry, alpha n. So come back here, and then insert alpha n. And all right, cool. So now we have 64. So we thought it was 56, and now this is popping out 64. 62 was off. And now this is saying 60. Oh man, yeah. This is tricky because alpha t was 3.7 and alpha n is bigger than that. Oh man, yeah. Should we just try to Maybe let's just guess the other direction. We're going to go 54 and see how much error we generate. So with 54, we're going to divide by 20, divided by sine 60. That's my alpha t. I'm going to store that as alpha j. And now I'm going to come over here and then use that alpha. Oh, is this what I'm not doing? Yeah. Oh, yeah. I didn't even. No, duh. I'm not even doing the iterative part right. Yeah. But let's say we thought it was. All right. We should really slow down. But what we did is we're now saying 54, and I guess we'll just stick with that. This gives us a time value at when that's going to happen. We're going to take that time value and throw it into here. Oh, no, you could do it that way. No, but we were saying no, that value of x, we were right. So 56 gives us that time value. So now we're going to throw in 56. Yeah, we were doing it right all the time. Negative tangent of 30. See, now this is where I'm going to make mistakes. Store that as alpha w. And now, yeah, I don't know where I got confused. But now we're going to go zoom 6 because that's in our calculator. And hopefully we get something pretty decent. Oh, it's wigging out. Oh, it didn't like that. But yeah, because there's a chance that this gives like a non-real number. Alright, yeah, let's see if it graphs. Alright, hell yeah, that time it did. And we go 0, we got a left bound, right bound. Okay, 3.72. So this is now my x value. My j value was 3.1, and my x, we're going to store that as alpha I. Alright, so, and then even just, I don't even know. Alright, this says if we actually do go 54 meters, it's going to take a lot longer for that to, to drop. So we actually need to increase this. And maybe we should have been increasing this the entire time. Because I don't think at any point... So yeah, well, let's go 70 meters, you know what I mean? Holy Toledo. Alright, so that's the whole point of, like, working with one problem, just to be like, well, are you getting any sense for it? You know what I mean? Hey, if this distance is 70, and it takes that much time to go this distance, you know what I mean? Well, like, what's the time to actually go the other distance in the y? You know what I mean? And these equations are separate. So even if I went out to here in the x, the other equation might be like, right here in the y. And then we're just trying to make these things meet. Okay, let's do it. So we're going to try to find our time value, and that's 70. Dividing by 20, dividing by sine 2, dividing by 60. Okay, so this is going to be, we're going to store that as alpha e. So this is my time value. Now I'm going to throw in 70 right here. And we got negative tangent of 30 times 70. I'm going to store that as alpha w. And now I'm going to graph. Alright, find the 0. Alright, we get 4.1 seconds. And what was alpha e? 4.0. Oh yeah, hell yeah. So now we're just we did it. You know what I mean? So now we have a time value. Yeah, we guessed right. It was so fascinating guessing wrong. Where you're just like, no, what are the outputs telling me? It's like, no. It's like if yeah, that was interesting. Like, what were the outputs telling me? They were saying that if I went like only 56 meters, and the time it takes to do that, oh yeah, that was interesting. it was saying that this lob would take a lot longer than just to go that distance. So we had to increase this distance, and then this kind of, you know what I mean? This goes longer, but now this starts to speed up and get there faster. So that's what it was. Holy but even just those relationships are just really hard to see from the equations alone. So we said if we had a distance of like 50 or 56, you know what I mean? This would actually get there pretty. It would get in the x direction fairly fast. You know, if that's all we were doing, that time was fairly fast. When we threw in, but due to continuity, if it went 50 meters this way, it had to go down in the y that direction, and the time to actually do that, it was much slower. So then we actually have to increase this x value to make that time like longer. But then because of gravity, this last part goes real fast, and then those start to equal out. And so now at 20 meters of height, we know that we can go out 70 meters in the x. And what's our y value? You know what I mean? And and so we have our y value was alpha w, and then we would go negative 40 meters in the y. You know what I mean? So that was our y direction. And if we wanted to figure our total distance, that's the Pythagorean theorem. So it's going to be 70 squared plus 40 squared, square root that, and we have basically 80 meters. So our distance for this problem is 80 meters. And finally, I think we've done it. You know, if we want to do the full-fledged solution, we know, you know, if we're going to throw letters at this, like we know that we have to be, like setting up this scenario, 20 meters per second, we have to be a distance of 80 meters. You know what I mean? And we had to check on reality. For sure, we have to be greater than 40. I mean, if you make huge... I was making huge errors where I was getting like 4.5 meters. You know what I mean? And I was choosing an initial velocity of 10 meters. It was only half, but still. I was just like, oh, no, something was off there. So that actually... yeah, it'd be fascinating to go back... But anyway, so I think we're done with this video. I mean, because, like, I just wanted to find a way to bet your life on it. You know what I mean? Could I bet my life that this distance is 80 and that I'm not off by a factor of 5? You know what I mean? You usually, sometimes, if you're going to not make errors by a factor of 10, hell yeah, you definitely don't want to be off by a factor of 10 in either direction. You don't want to say this is 8 meters or 80 meters. But yeah, I'm very satisfied. Very satisfied. You know what I mean? And even from the perspective, yeah. And there was one other way that I did this with 3, 4, 5 triangles. But I don't know, you know what I mean? Those are your go-to. If you're doing trigonometry, you know, you have a 3, 4, 5 triangle. Sometimes that's useful. I just did 30, but yeah, how we solved this was, and we still, like, this is actually not accurate to 100%, because what was the huge assumption we made? We said velocity in the x was just the 20 meters, you know what I mean? But we know that's not the case. So we know that it ain't going to go that far in the x, so that we know this distance is now less than 80. But because of that, we have a top end. You know what I mean? We can bet our lives that the distance is between 40 and less than 80. You know what I mean? Because we overshot our velocity in the x. And if we even mentally, you know, say that, you know what I mean? If our velocity in the x was like way greater, we can go a lot farther in the x. For sure. But if our velocity is slower in the x, we're going to get less distance in the x. Yep. So just 100%, I'm pretty confident that our answer is going to be between those. Okay, hell yeah. So I think I'm going to do 2 parts on this, because I want to go through, like, because the other thing, could I do this entire problem with just letters? You know what I mean? Knowing that I'm not using any sort of numbers that help me get a general view, or sometimes a better view of what's going on. Like that's what numbers do. You know what I mean? That's why we chose 20 meters per second. 1 second, that's going to be a velocity in the y of 10. and then we know it's going to go up for a second, down for a second. So if we knew that we were on our horizontal, it's just going to take 2 seconds. But because of the slope, it can stay up for a total of 4 seconds. But we still know that that's BS, that our actually time of impact will actually be probably like 3.5 or 3 or something like that, because we overshot. We said our velocity in the x was much greater than it was. But that was a pretty good approximation. Actually, I'd be surprised if it's not too far off. If it's like 75 meters, I'm going to pat myself on the back and keep using this approximation for a lot more things, just because it's very useful. And again, the approximation is, hey, if you have sine 30, yeah, obviously that vector is half, but this other vector, just say it's 100%. Okay, so hell yeah, we did 1 page, and it looks like a mess. But anyway, thanks for joining me, and guess what? That's a video.